Hello, welcome to our video on osmosis. Before we get started, I want to make sure that you have already checked out our video on diffusion. That's an important video to watch before we get into osmosis. Just to recap though, I want to point out where we see our fluid compartments. We have our intracellular fluid, the cytosol, the fluid inside the cell, and then we get our extracellular fluid, which is going to be the sum of the interstitial fluid that we see in between the cells and the plasma that we see make up the blood. For osmosis, we're going to be discussing the movement of this fluid across the membrane. And if you recall from diffusion, we were talking about the solutes, the particles. This time we're talking about the solvent, water entering and leaving the cell. We had mentioned diffusion being in two forms, simple and facilitated, and they were going to be dependent on the membrane being permeable to those solutes. And if that was the case, those solutes would diffuse across that membrane from a high concentration to a low. For osmosis, we have a membrane that is no longer permeable to those particular solutes. Now, one membrane can be permeable to some solutes and not others. That's perfectly fine. But it's the solutes that can't cross the membrane that result in a driving force for osmosis. If we get solutes that cannot cross, then we will start to see the solvent cross the membrane in order to dilute that particular solute. So in other words, if we can't move the solute across the membrane, we move the solvent across the membrane to accommodate for it. Also, recalling back to diffusion, we saw that all the different solutes involved didn't influence the transport of the others. They behaved independently. When we look at osmosis, however, we look at the sum of the particles that are going to be involved. It doesn't matter if we have 50 different molecules that can't cross the membrane or 50 of the same molecule that can't cross. They will all exert the same influence. So we look at them as a sum. And because of that, we have to change a couple terms. One is going to be, we don't use concentration, we're going to use the term osmolarity. Concentration implied a particular amount per volume that we had of a single solute. Because here, the independent solutes don't matter, it's the sum of the influencers that matter, we use the term osmolarity. One fluid can have a higher osmolarity than another. We see the term osmotic pressure. When we move fluid across a membrane, we can apply a force to push that fluid back to where it was. The amount of pressure needed to equalize out that driving force pushing the fluid across initially is going to be the osmotic pressure. And finally, we'll talk about the nature of the extracellular fluid. We'll have some terms to describe that fluid as it compares with the intracellular fluid. So again, osmolarity. Concentration-esque. When we use concentration, we talked about one particular molecule. There are going to be three terms or three things to consider when we talk about osmosis that we didn't have to bring into account when we talked about diffusion. The concept of osmolarity, we'll use this in exchange for the term concentration that we had earlier. We have osmotic pressure, and we have to describe the nature of the extracellular fluid as it relates to the intracellular fluid. Osmolarity describes the amount of solute we have that cannot cross that membrane. In diffusion, every single solute behaved independently, as if the others weren't present. Here, we take the sum. It doesn't matter if we have 50 different solutes that can't cross, or we have 50 of the same solute that can't cross. They all will exert the same influence for osmosis. So we throw away the term concentration for a while, and we use the term osmolarity, because it encompasses all of the solutes that cannot cross that membrane. So if we're looking at osmolarity of this particular situation, we look at the left-hand side of that cell compared to the right-hand side. We have four different solutes, X, Y, Z, and W, outside of that cell that cannot enter by diffusion. On the right, we have 4 of the same molecule. We have 4 X's. Both of these create the same osmolarity. It's the same kind of environment with respect to osmosis. It doesn't matter if we have 4 different solutes or 4 of the same solutes. 4 is 4. And as long as all of those cannot cross the membrane, they will all have the exact same influence as far as osmosis goes. Likewise here, we see an environment where we get an equal degree of osmolarity. Here we still have 4 different types that cannot cross. The Z and the W can't exit. The X and the Y can't enter. On the right, we still have 4 X's. They are where they are. They cannot go across that membrane. So again, osmolarity, same situation on the left and right. It's the total number of particles rather than how many of individual particles that we have. Osmotic pressure is going to be a term used to describe the force at which that solvent moves across the membrane. And it can be calculated. We have a constant times the temperature times the osmolarity that we're seeing in a particular environment. And we can set up an experiment with one of these U tubes, not the videos, the chemistry apparatus, where if we put a semi-permeable membrane in the middle of this U tube, equal amounts of fluid on either side, but we put a solute on 1/2 of that U tube, and that solute would not be able to cross the membrane. What we would see is we would see osmosis occur where the fluid, the solvent, would cross that membrane over into the side of the U tube that has the higher concentration of solute particles, the higher osmolarity. If we applied a pressure on the left-hand side of that tube, we could force that fluid to cross back over the membrane. The force necessary to equalize out those fluid levels again would be considered the osmotic pressure, and it would give a reference to the amount of fluid force we had with that fluid moving from right to left to begin with. If we're describing the nature of the extracellular fluid, we have 3 terms in which to deal with: isotonic, hypotonic, and hypertonic. Now, all 3 of these terms describe the extracellular fluid when compared with the intracellular fluid. Iso, as a prefix, means same. So if a cell is in an isotonic environment, that implies that the solute osmolarity outside the cell is the same as the solute osmolarity inside the cell, in which case we would get no solvent movement, we would get no osmosis. A hypotonic, hypo meaning below or less than, is describing the extracellular fluid in the sense that it has a lower osmolarity than the intracellular fluid. Osmosis will always occur from a low concentration to a high concentration of solutes. So in this case, with the external being lower, water will move into the cell. Hypertonic, hyper meaning more than or above, implies that the extracellular fluid has more solutes or a higher osmolarity, in which case water again moves in the direction of that higher concentration or higher osmolarity. So we see more of the solvent leave the cell and move into the extracellular regions. So here would be an example of what would happen to a red blood cell if put in some of these different hypo or hypertonic environments. In the middle, we see a normal red blood cell. And for those of you that don't know, a red blood cell has a biconcave structure. It means if we took it and we pinched it, we put an indentation into the top and the bottom. That's what we see with a red blood cell. As we move to the left, those red blood cells have been put in a hypotonic environment, meaning the osmolarity is greater inside the cell than outside. Therefore, by osmosis, solvent enters the cell and makes them become bigger. So the first thing we lose is that biconcave structure. They lose that indentations on the top and the bottom as they engorge and become more round. They continue to take on water until eventually, you barely see it up here at the upper left, a red blood cell ghost. That cell is stretched so thin that it barely even shows up when put on a slide. If this continues, that cell can only hold so much water. It will rupture and lyse, and then the cell will be dead. Towards the right, we see the opposite scenario. We see a red blood cell put in a hypertonic environment, where the osmolarity is greater outside the cell than inside. In such a case, water leaves the cell and the cell begins to crenate or shrink. So here we start to see the spiculated appearance of some of that internal cytoskeleton is protruding outward against a shrinking membrane. If that continues, the cell's only got so much fluid to give up. It loses its ability to maintain homeostasis inside the cell, and again, the cell dies. So when we go back to talking about homeostasis, we want to make sure that these cells are in an environment in which they can function properly. So we want to maintain the environment around that cell so we can keep them functioning. We have various osmoreceptors always detecting the thickness of the blood or how concentrated that blood is, to go back to that term one more time. But remember, any regulation of blood osmolarity is not specific. It's the sum of all the solutes in the blood, not any one solute concentration. And we have a negative feedback control for that particular regulation. So when we look at a dehydration scenario, we see a decreased volume of the extracellular fluid, and as we lose that volume, the solutes in that fluid give a greater osmolarity. So we will see a couple of things happen from there. We will see an increase in the osmolarity detected by the chemoreceptors in the hypothalamus, the thirst center. We'll also see a decrease in saliva production, giving you that dry mouth and this thirsty sensation. Both of which becoming a driving force for you to consume more fluids to replenish the fluid lost in the body. The water gets absorbed through your GI tract, increasing the volume of fluid that's in that extracellular compartment and decreasing the osmolarity. That's going to basically counter what we saw with the dehydration state, allowing the osmolarity and the volume of the blood and the extracellular fluid to go back to normal. I want to thank you for watching. Hope it helped.